All right. So how I would approach ranking molecules is to figure out what's your most and what's your least acidic. So here you have all these rings, and first and foremost, I would compare your alcohol to your carboxylic acid. What's more acidic, your carboxylic acid or an alcohol? Carboxylic, yeah. So you know the two on the right are gonna be your on your higher end in terms of acidity for this question. So in looking at these two on the right, um, which one is more acidic? You have one with some fluorines and ones with just your carboxylic. Yeah, and so automatically you know that this one is your most acidic. This one comes second in line. Can anybody tell me what's your least acidic out of all these? Yeah, the second one. As you can see, carefully looking at it, it looks like all these are the same, but this one isn't a benzene ring. This one doesn't have these pi bonds inside the ring to further stabilize it. So in comparison to the others, even though this has oxygens which are more electronegative than a methyl, it doesn't have these pi bonds within the ring. So this would be your least acidic. So that's how I would approach it. So does anybody have questions on that? Because I'm pretty sure, I mean, I didn't take the test, but I'm pretty sure, I mean, when I took it, I got a few ranking questions. And I know if you can figure out what's least acidic and what's most acidic, you can at least, cross off half your choices. So is there any questions on this? No. Okay. All right. So just comparing two molecules, you should be able to figure out what's more acidic and thus least acidic or more basic. And so just looking at this, what's more acidic? These are just straight cardio. One person says the one with the fluorine. Does anybody concur? Yeah. So the one on the right, the one with the fluorine, because that's the only thing that's different. You're comparing a fluorine to a carbon. You know that from cardio, things that are bigger of an atom, more electronegative, this and that. It'll be more acidic. Next up, pretty much the same question, but you're comparing a nitrogen or nitro group to a carbon. So what's going to be more acidic? Yep, the one on the right. So looks like you guys are pretty solid on that. But these are from your textbook. Did this come up on your exam at all? This one? All right, so unfortunately, this is somewhat of an Orgo 2 concept. It has to do with resonance. You would intuitively think that this one has more of a dipole pointing upwards, but when you do the resonance, yeah, this has nothing to do with cis and trans. It has more to do with the position of the which carbon on the ring that the groups are in. So I'm not going to break the whole thing down here, I would just remember, in case it comes up again, that these two positions here directly next to your substituted group or directly across your substituted group are your acidic positions. This one in blue is not. All right, so this again is more of an Orgo-2 concept. It has to do with resonance. If you were to break it down, you would somewhat find that these electrons have a hard time getting to this position here, but can very easily get to these positions in red. So if you have a substituted ring, the positions that are directly next to or directly across will be your acidic positions. So everybody get that? All right. And this is just asking, what is your acid and base? I've seen this in bonding, so it's just cardio, really. So what's our acid? Someone says the acid is with the carbon, is the positively charged carbon. Does anybody else agree? So yeah, the carbon on the left side of the reaction here is our acid. Why? It's because we can just look at cardio. Things with a positive charge lack electrons, and if it lacks electrons, it wants them. And we know that acids are species that accept electrons, and so that is why that carbon will act as your acid. And thus, the water molecule will be your base. These electrons on the water will be what bonds to that carbon, which is where you get this from. Any questions on that? No? Okay. So curved arrows, how I would approach it is, again, I would just, determine what's your acid and what's your base. So looking at this problem, what's your acid, what's your base? Yeah. Your HI is your acid. And so in here you have, again, this is key. What I'm doing here is when you get your assignment, draw all your bonds out. So there's a person that sent me a message yesterday, like asking me, like, can I do this again, this and that. He basically did it all wrong, but he claimed that he couldn't do the arrows. Draw all your bonds out. So instead of just an OH, draw your O with your sigma bond. And it just makes everything easier, and it allows the system to better visualize what you're doing, and this also allows you to more easily use the arrows. And so if HI is your acid, your I is what is pulling electrons towards itself. So that's what's going to occur. And thus you're left with a partial positive charge on this hydrogen. What do we know about positive charges? It wants electrons. Where is it going to get those electrons from? The oxygen. And that is why you're left with the products that it gives. So your iodine is, as expected, floating around by itself. And now you have a oxygen with 2 hydrogens coming off of it. We know that a oxygen with 3 bonds has a positive charge. Questions?
Yeah, and just to add to that, I mentioned this on our Monday class as well. I'm sure you already kind of did this, but keep in mind for this week's activity, when you're grabbing something, so when the base is attacking your acid, you're always going, the arrow is always starting from the lone pairs and is going to where it attacks. And this is a very important thing to remember, because if you do it the other way around, if you do the starting of the arrow from the hydrogen and the arrowhead to the oxygen, that just means that the hydrogen attacks the oxygen, which doesn't really make sense. Okay, so you want to start from the oxygen and go and attack whatever you're attacking. So keep that in mind.
And again, arrows always indicate the flow of electrons. So when you do your assignment, do not start an arrow at an atom. So it's not the oxygen that's attacking the hydrogen. It's the lone pair that's bonding with the hydrogen. And so, like this previous example, that's exactly what's happening in this one as well. The BF3 looks somewhat like this. You guys have drawn this out probably 100 times already. And so the lone pair from the oxygen is bonding to the bromine, and that is what we see in the products. So it's not taking away anything, it's simply bonding to, it's making a bond with the fluorine. I mean the bromine. So your product still has your ketone, but that oxygen is again bonded to your bromine. And what charge does this oxygen have? Man, that's unfortunate. All right, so apparently I must have said something wrong. An oxygen with 3 bonds will always have a positive charge. And that's something that's key, especially for your bonding assignment. Always indicate if there is supposed to be a charge, place a charge on the atom. So yeah, Alex, you got it. They did the formal charge formula. So you have your 6 minus 3 because of your 3 bonds and the 2 electrons that are left, you're left with a positive charge. An oxygen with only 1 bond, for example, OH, an oxygen with only 1 bond will have a negative charge. 1 bond is a negative, 3 bonds is a positive. Aqueous. What does aqueous mean? Water. So what's going to happen with the metal, the sodium? Dissociate, right? So just like salt water, if you were to throw table salt into water, those 2 ions would dissolve away. So in water, anything on the left side of the periodic table will dissociate and just be floating around in solution. So I just act like that Na is not even there. And now you have an OH. Can somebody tell me the charge on this? Negative. All right. So just to draw this out, again, it's very good to draw out your bonds. So this should be a carboxylic acid. All right, and so you have, so what's your acid, what's your base? Again, just thinking this thing through. What's your acid, what's your base? Yeah, OH is the base. So in general, if you see a species with a negative charge, it has a lot of electrons on it. So it can use them to bond with something. Thus, it's your base. So your OH is your base. It has a negative charge. It wants a proton to get rid of that negative charge. Where is it going to get that proton? Your carboxylic acid. And this oxygen is electronegative. It's going to pull the signal bond electrons towards itself. And thus, the products are simply water. And this, what used to be carboxylic acid, is just without the hydrogen. And again, always draw your charges. Makes sense? The next one is really the same thing. Any questions? All right, so did you guys get something on your exam? You're probably going to see it, but a reaction that doesn't occur because of whatever reason? All right, so here you guys probably already know that because because it was in your textbook, this reaction doesn't occur. Why? So I would look at pKa's. So here is our base, right? And the question is that strong enough? So here you have that with ethyne, which looks like this. This carbon that's bonded to the hydrogen isn't electronegative. So there isn't a draw towards itself. It's not pulling the electrons towards itself. There isn't really a partial positive on that hydrogen. And so there's no real reason why it should give it up, right? And so this would be a, this is tightly bonded to that carbon. There's a very strong bond between these two. So again, it's not really going to want to give up that hydrogen. So you're going to want a strong base. And is this strong? And before we get, dive into chapter 6, you guys will have, rules of thumb to figure that out. But I would just look at a pKa table. Hopefully he gave that to you guys. But the pKa of this is around 16, and the pKa of this is around 25. So what's our trend? The smaller the pKa, the what? Yeah, the stronger the acid. But this is supposed to be acting as our base. So this thing is a stronger acid than the thing that we're trying to take a hydrogen from. That doesn't make sense, right? A base is going to want to attack that hydrogen. But if it's not a strong enough base and it's instead a stronger acid, it's not going to want to do that, right? And so, again, this reaction isn't going to occur for that reason. And later on, you guys won't really have to look at a pKa table, but in order to find something that will deprotonate, you're often going to see that term deprotonate, which is just simply taking a hydrogen off of something. You want a stronger base, which means a higher pKa. The pKa for something needs to be higher in order to deprotonate the other species. Does that make sense? This is often a question, and the person I made an example out of is actually asked me about this question. Again, you want to draw everything out. So you have an ethanol with a methyl lithium. A methyl lithium is simply, don't overthink it, it's in and of its name. It's a methyl with a lithium. But what's going to happen with that lithium? It's going to dissociate. So that is just floating around. And thus, when that dissociates, you're left with a negative charge on the methyl. So the methyl is still CH3, but with a lone pair negative charge, right? Because it dissociated. And you have your ethanol. So can somebody tell me what's going to happen? What's your acid, what's your base, and what's going to attack what? CH3 is the base. Yep. So what's going to happen? It's going to use that lone pair to what? Lone pair will attack the hydrogen, right? So again, it has a negative charge, and what's it going to want to do? It wants to fulfill that negative charge by gaining a proton. It's going to gain that proton by using that lone pair to attack that hydrogen. Right? All right, and so here you have these hydrogens are going to come on to, those electrons are going to come onto the oxygen itself, and thus your products will be a neutral CH4 and an alkoxide. Again, on your bonding assignment, always indicate charges. So you have your charge there. And
So
you also
Robert,
your lithium
Robert on the
floating around.
chat. Sorry, Michael. He says acid always attacks the base. That's incorrect. The base always attacks the acid. In this case, your CH3 is going to be your base, and your ethanol is going to be your acid.
Yeah, and so remember from our definitions of acid and base, our Lewis acids accept electrons, and that is what this alcohol is doing. It's accepting electrons from this methyl ion. All right, and so in your bonding assignment, there should be a plus symbol, so it's just indicating you have an ethanol plus your methyl ion plus the lithium. We react it, and we get what we got. Any questions on this? And just a helpful tip for your bonding assignment, you'll see on the left-hand side of the system, if you guys haven't been seen it yet, you'll see a positive and you'll see a negative. The negative, just click it. If you click your negative and you click the atom that you want to make a negative, like your OH, if you were to click your negative and just then click the oxygen, it should, at least in my experience, takes away that hydrogen for you. All right, but again, always indicate your charge. Moving along, this one should be relatively easy. What is the stronger acid? Okay, now do you guys know the reason for that? Yeah, it's directly attached to the ring, and so if you were to do its conjugate base of that is simply this with the ring, right? And so these electrons will easily be put into the ring, thus make it more stable. Instead of this has this extra carbon in between, which doesn't really want to accept those electrons, right? So that is why A is your stronger acid. Next, which one of these is your Lewis acid? You could eliminate half of them with cardio.
Also, guys, notice 3 of them have a negative charge on that. No, 2 of them have a negative charge on them. And you know that NH3 has the potential to create 3 bonds and has a lone pair. So what does a negative charge usually tell you guys?
Yeah.
Okay.
So
perfect.
We're going to eliminate half of these. All right. So with that in mind, what will be our acid? So people are saying A, people are saying C. What to think about is whether or not, again, the key here is Lewis. All right. And so with Lewis, you're accepting electrons. All right. And so this nitrogen already has a full octet. It's not positively charged or anything like that. It has a full octet. And so it's not going to want to accept more electrons. Otherwise, it would then be unstable. Also, this could be considered a Bronsted because you have these hydrogens to play with. But strictly when it comes to Lewis, A would be your best answer. Or do you have any comment on that?
Yeah, that's basically it. So guys, be careful. If you see a negative charge, you know that for sure is a base, right? Because bases have extra electrons and they want to donate. Lewis acids want to accept. Now, AlCl3 as well as BF3, for example. Anything on that group 3 is going to create this 3 bonds, and they're never going to have an octet, and that's okay with them, right? But they're always going to be considered Lewis acids, right? Because they don't have that full octet and they're willing to accept electrons. So keep in mind, if you have a negative charge or a lone pair, remember lone pairs are the ones that attack and grab something. So in that NH3, you have that one lone pair that is able to attack or to donate those electrons to an acid. So every time you have a lone pair or a negative charge, you have electrons able to be donated. So that thing is going to be a base. While if you draw out AlCl3, you're only going to have those 3 bonds to Cl. You're not going to have a lone pair. So that would make it electron deficient.
All right. And lastly, came up with this last minute. Somebody sent me this question because they encountered it on the exam. Did anybody encounter this one on the exam? All right. So if someone is so confident, can they tell me which one is the stronger acid? Someone said B because it was electronegative. All right. So unfortunately, it would be the nitro group. Yeah. So it comes down. He should have, if he's going to test on it, he should have went over it in lecture, but usually he sucks like that. But it comes down to electron withdrawal. Right. So your electronegative atom, this is very electronegative, but it won't, in comparison to the nitro group, it's not going to be as electron withdrawing compared to the nitro group, because it comes down to like a collaborative effort. So these 2 oxygens are able to hold as a whole more electrons than just the halogen. So, and also a nitrogen with 4 bonds, what's the charge on a nitrogen with 4 bonds? Positive. And so what do we know about positively charged atoms? Do they want electrons? Yes. And so a positive charge is going to draw electrons towards itself, right? And you have these electronegative atoms. So as a whole, this nitro group will be pulling electrons more so towards this group than just the halogen itself. Does that clear things up for you? All right. So as I said, this session would be relatively quick. So that's personally all I have for you today. Is there anything unclear about this document that I went over? If not, and you guys are good, I'm going to be here for 10 more minutes or so. So definitely just feel free to ask anything you guys want to know.